Hi, today we are going to talk about what is meant by elasticity. Okay, so let us, so we first have to, in order to describe elasticity, we first have to get an idea of what is meant by a configuration of a body. So I want to make sure that we understand this. A configuration of a body is the arrangement of each of its particles in specific locations. It can be applied to discrete or continuous set of particles. For example, this is a particular configuration of a string of particles. The particles are labeled with their colors. So you can see that the brown particle is in one place, a red particle is somewhere else, a yellow particle, and so on. So this is one configuration. This is another configuration. You can see brown is somewhere, red is somewhere, and so on. So I just want to make sure that you understand that every particle has to be labeled and their location has to be given. So for example, if you look at this one, it looks identical to the first configuration, correct? But there is a difference because the purple particle is in the second position and the red particle is in the last position in this one. So this is a different configuration because what it means is that the two particles have exchanged positions. So this is a different configuration. This is one dimensional. Let us look at what happens in multi dimensions. So if you look at finite element methods or other methods, what happens is we have millions of particles, but they are still finite. So what we can do is we can label the particles 1, 2, 3, 4. That's the labeling. And I tell you where the coordinates are. So that's how we do for these kinds of things. When we get to continua, even this labeling system cannot work. In the first one, we had colors. The second one, we had numbers. Now we are really stuck. So what it is that when we have uncountably infinite number of particles, what we do is we use one shape or one configuration to label the particles by their locations. So the first configuration, original configuration, is what I use for labeling the particles. And the second one is what I use to show how the configurations are deformed. So I always have to start with one configuration and use that for labeling. Okay, so once we know what a configuration is, now we can talk about what are common definitions of elastic bodies. For example, elastic body in many books, and in fact in elementary texts, it will say that the capacity of a body to return to its original shape. This is not elastic because of two things. The body may not have any particular original shape. Only solids have, fluids don't. For example, a gas doesn't have an original shape, but it is elastic. Okay. On the other hand, there are bodies which can creep, but can still return to their original shape. These are called viscoelastic bodies. So what even is an elastic body? So the definition, it gets closer, is that if I apply a constant force, I should get a constant deformation. Right? So now we will formalize this by saying that our definition of elastic body will be based on which two versions, one of which can, at least one of which can be tested. So first one says a body in which the forces throughout the body depend only upon the current configuration of the body and nothing else. Roughly, if you know where every particle is, you can tell what the internal forces are. For example, an extreme case of this is molecular dynamics, where once you know the position of every particle in the molecular dynamics simulation, you know all the interaction forces. So that is an elastic body. All molecular dynamics is based on elastic bodies. Okay. Now, a body when subject to known fixed forces assume fixed shape. So this one says if I know the force, I can tell you what the shape is. This is an elastic body. I'll show you an example of how you can use one of these things to decide whether a body is elastic or not. So if you look at this particular test, I'm going to apply a known force, and you can see that the shape of the body is not fixed. So I cannot tell the shape of the body by knowing the force because it depends upon what time it is. You can see that actually if I change the force, the shape changes, but still it is never the same shape. If I wait for a while, it changes. Okay, so that's what we mean by a body not being elastic. So this test actually works for all these bodies. Okay, so now we get to the fact that elastic body is not a real body. What I mean by that is It is an idealization or a cartoon. So to give you a clear idea of what this means is that we usually think that a rubber band is elastic, but in reality, when subject to a force, it slowly creeps and has a hysteretic response. There is more than one shape for a given force or more than one force for a given shape. In fact, I'll show you what I mean. This is the actual response for a rubber band. You can see that it has some hysteresis. You can see the loop. So now I will show you how we can use our definition to conclude the body is not elastic. So we fix a force. If I draw a horizontal line, can you see that there are two shapes for a given force? Also, if I draw a vertical line, there are two forces for a given shape. So what it means is that if I know the shape, I cannot tell you the force. If I know the force, I cannot tell you the shape. That is why it's not an elastic body. However, we may still idealize it as one by just kind of ignoring the hysteresis. This is what we actually do. So please remember that all our bodies, elastic bodies, are meant to be cartoons or idealizations. Okay. Now, the question for us is, how do we quantify this idea? Up to now, we have been talking in generality. So now let us start looking at quantification. So we need a way to quantify the shape of a body. Then we need a way to quantify the forces. That's easy. We have done this from statics, so that's pretty easy. For example, for an ideal spring, we are choosing to quantify the shape of the body in terms of only one parameter, which is the length. That may not be actually correct, but that is enough for our purpose. So now we are going to say that for elastic body, the force is only a function of the length. So now you can see, if I give you the shape, length, I can tell you the force. So if you look at a simple spring response now, you will see that there is there's some curve, and that curve is given by some function f equal to g of L, and the place where it crosses the x-axis is called the natural length, L naught. We can use that in a convenient way. For example, if I want to talk about a linear spring, then by the way, the natural length is the length when there is no force applied. So for a linear spring, you can see that I have F equal to K times L minus L naught. K is called the spring stiffness or the spring rate, and that tells you how stiff or soft the spring is. That is the stiffness of the spring, and you can see it depends upon L minus L naught. You can see it represents that straight line. That is how we do. So it has two parameters, natural length and stiffness. But now we have to take this idea which we know from our basic physics class and try to generalize it to a 3D material. So what do we have to do for that? We need a way to quantify configuration and shape of the body. Now it is in 3D, it's an uncountably infinite number of particles. We cannot use one particle, one parameter and so on. So this is what we are going to spend a lot of time with. The functions that we come up with this are called shape functions. They're also at the heart of finite element methods and all of that. So pay attention to this. Then we need a way to describe the force distribution of the body. This is called kinetics. We are more familiar with it from our previous undergraduate classes, but so this will be much briefer. Then we need a way to connect the forces to the configuration. And what we are going to do is what is called generalized Hooke's law. Okay, this you are somewhat familiar with, but not fully. So we're going to spend some time on this. Then we need to find a way to find the shape given only the external forces. If I know all the forces, I can just use Hooke's law and I can connect the force distribution to the configuration. Unfortunately, in most of these cases, we only know external loads and maybe some constraints. So we need to find out what's inside. For that, we need one more piece, which is called the equilibrium conditions. Then we'll connect all of these things together and we'll land up with a way with differential equations. And then we have to figure out a way to solve it. This sequence is what we are going to cover for the next 13 weeks. Okay, thank you very much.